As the need for lighter structures increases, engineers use thinner sections. Such sections need to be designed to prevent or account for buckling. The simplest form of buckling occurs in pin-ended columns. Up to a certain load, the column can take the applied stress in compression. Once the critical load has been reached, the column bends. Increases in load cause increase in deflection and more bending. The column fails suddenly. It has no post-buckling reserve of strength. Plates buckle in a different manner, by stretching of the membrane between supports. Lateral deflection is prevented by edge restraint. The plate fails gradually under increasing load. Plates with edge restraint have a post-buckling reserve of strength. In this test, the beam is loaded using the weights here. The top flange of the beam is in compression. The flange is a thin plate and will buckle. Buckling does not cause collapse. The phenomenon is elastic. Remove the load and the plate recovers. But because the plate has buckled, it becomes less stiff. The edges of the plate must work harder because the middle cannot take the stress. This longitudinal stress distribution is difficult to analyse as it depends on several variables, such as the size of plate. The buckled plate may be thought of as two narrower plates. This stress distribution is easier to analyse and is known as the effective width concept. Wide plates buckle more easily than narrow plates. Buckling coefficients may be derived to quantify the ease with which a plate buckles. These coefficients depend on the aspect ratio of the plate. Once the aspect ratio is greater than 1.5, the plate would rather buckle in a smaller waveform. Notice that the lowest buckling coefficient is 4. This is the safest to use in design. We have now inverted the original test beam. One edge of the plate is unsupported and therefore buckles very much more easily. Plates with one edge unsupported have a buckling coefficient of 1.328. Most plates are unlikely to be perfectly flat. Even without load, this plate is slightly buckled. I'm now going to load the beam. Buckling starts earlier and causes a reduction in ultimate load. To be safe, all plates should be assumed to have some imperfection. Plates subject to shear loading also buckle. The analysis is very complex, but may be approximated. Tension field theory is used to analyse plate girder webs. To summarise, many structural elements may buckle under load. Plates have a post-buckling reserve of strength that may be used in design. Effective width concept may be used. Buckling coefficients are used to predict the start of buckling. All plates should be assumed to have initial imperfections. Shear buckles in plate girders may be analysed using tension field theory.